सदा सदा पुरनूर रहे। गुरु नानक देव विश्वविद्यालय, गुरु नानक देव विश्वविद्यालय। सदा सदा पुरनूर रहे, पुरनूर रहे, पुरनूर रहे। गुरु नानक देव विश्वविद्यालय। अनहत नाद बजे, आहत जलन बुझे, अमृत शब्द वरे, तन मन तीन हरे। सदा सदा पुरनूर रहे, पुरनूर रहे, पुरनूर रहे। गुरु नानक देव विश्वविद्यालय। धरती अंबर पवन समुंदर सूरज चंद सितारे, एक दी तुन विच गावन वावन राग इलाही सारे। सत सुहान सदा मन चाओ, सत सुहान सदा मन चाओ। एह गुरवाक उजाला, सदा रहे परगास रूप। गुरु नानक देव विश्वविद्यालय, गुरु नानक देव विश्वविद्यालय। चिंतक सिरजक रसक विनोदी, सहज निमर विसमादी। निर्मल निरपौ सच दा खोजी, विगसे आद जुगादी। रोशन हो वंडे रुशनाई, रोशन हो वंडे रुशनाई। दिखया पावन वाला, गुरु नानक देव विश्वविद्यालय, गुरु नानक देव विश्वविद्यालय। जिथे मिलदी ओट ने ओटिया, पौंदे मान ने माणे। ओह दर उसदा, ओह कर उसदा, एह गुरवाक वखाणे। जिथे मिलदी ओट ने ओटिया, पौंदे मान ने माणे। ओह दर उसदा, ओह कर उसदा, एह गुरवाक वखाणे। ओथे नदर मेहर दी होवे, ओथे नदर मेहर दी होवे, जिथे नीच समाला। गुरु नानक देव विश्वविद्यालय, गुरु नानक देव विश्वविद्यालय, गुरु नानक देव विश्वविद्यालय, गुरु नानक देव विश्वविद्यालय। नानक नाम दा ताज इलाही, सीस सजावण वाला। जिस दी होंद च शब्द गुरु दा, जगे पुनीत उजाला। सदा सदा पुरनूर रहे, सदा सदा पुरनूर रहे। गुरु नानक देव विश्वविद्यालय, गुरु नानक देव विश्वविद्यालय। सदा सदा पुरनूर रहे, पुरनूर रहे, पुरनूर रहे। गुरु नानक देव विश्वविद्यालय। अनहत नाद बजे, आहत जलन बुझे अमृत शब्द वरे तन मन तीन हरे सदा सदा पुरनूर रहे पुरनूर रहे पुरनूर रहे गुरु नानक देव विश्वविद्याला। धरती अंबर पवन समुंदर सूरज चंद सितारे एक दी तुन विच गावन वावन राग इलाही सारे सत सुहान सदा मन चाओ सत सुहान सदा मन चाओ एह गुरवाक उजाला सदा रहे परगास रूप चिंतक सिरजक रसक विनोदी सहज निमर विसमादी निर्मल निरपौ सचदा खोजी विगसे आद जुगादी रोशन हो वंडे रुशनाई रोशन हो वंडे रुशनाई दिखया पावन वाला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला। जिथे मिलदी ओट ने ओटियां पौंदे मान ने माणे ओह दर उसदा ओह कर उसदा एह गुरवाक वखाणे जिथे मिलदी ओट ने ओटियां पौंदे मान ने माणे ओह दर उसदा ओह कर उसदा एह गुरवाक वखाणे ओथे नदर मेहर दी होवे ओथे नदर मेहर दी होवे जिथे नीच समाला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला। नानक नाम दा ताज इलाही सीस सजावण वाला जिस दी होंद च शब्द गुरु दा जगे पुनीत उजाला सदा सदा पुरनूर रहे सदा सदा पुरनूर रहे गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला सदा सदा पुरनूर रहे पुरनूर रहे पुरनूर रहे गुरु नानक देव विश्वविद्याला। अनहत नाद बजे आहत जलन बुझे अमृत शब्द वरे तन मन तीन हरे सदा सदा पुरनूर रहे पुरनूर रहे पुरनूर रहे गुरु नानक देव विश्वविद्याला। धरती अंबर पवन समुंदर सूरज चंद सितारे एक दी तुन विच गावन वावन राग इलाही सारे सत सुहान सदा मन चाओ ओ, सत सुहान सदा मन चाओ एह गुरवाक उजाला सदा रहे परगास रूप गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला चिंतक सिरजक रसक विनोदी सहज निमर विसमादी निर्मल निरपौ सच दा खोजी विगसे आद जुगादी रोशन हो वंडे रोशन हो वंडे रुशनाई दिखया पावन वाला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला जिथे मिलदी ओट ने ओटिया पौंदे मान ने माणे ओह दर उसदा ओह कर उसदा एह गुरवाक वखाणे जिथे मिलदी ओट ने ओटिया पौंदे मान ने माणे ओह दर उसदा ओह कर उसदा एह गुरवाक वखाणे ओथे नदर मेहर दी होवे ओथे नदर मेहर दी होवे जिथे नीच समाला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला
So, hi everyone. Dr. Santra, are you there?
Yes.
Yes. Your video is off.
Yeah, I'm just going to make it on.
Okay.
So,
Hi. So maybe it's already 4. Maybe we can start. And I welcome everyone who has joined here on YouTube. I see there are few people who are watching us on YouTube and they are joining. But since it is already 4, maybe I can start with an introduction and meantime more people will join. Yeah. Okay. So a very warm welcome to all the Science Club members and those who have joined us from other institutes as well. This is a webinar series which Science Club Cyrox has been organizing during the COVID times, and we have organized around 20 to 25 webinars, if not. Yeah, I mean, I might be underestimating the number of seminars, but we have done a number of seminars, and that's the good thing we liked about technologies. So today we have a very special speaker, Dr. Bodhaditya Santra, who is from IIT, and I would briefly like to introduce him. He is an assistant professor at the Institute of Indian Institute of Technology, Delhi, IIT Delhi. He's a professor of physics, and his research group at IIT is building experiments to explore cold atom quantum technologies to address various problems in society and industry. This is a very upcoming field which is getting a lot of attention these days, and he's working on that field. So it will be very interesting to know more about this field, especially in India, and what are his plans. in this upcoming talk. Very briefly about him, he studied physics at the University of Burdwan. So I don't know how exactly it is pronounced.
Yes, Bardhaman in West Bengal. Yeah.
All right, okay. And after that, he studied at IIT Kharagpur, India. In 2008, he joined the group of Dr. Lawrence Wilman and Professor Klaus Jungmann at the University of Groningen, Netherlands, to work on laser spectroscopy of short-lived radium atoms. In 2013, he received his PhD degree for the thesis work on precision spectroscopy of neutral radium towards searches of permanent electric dipole moments. From 2013 to 2016, he worked as a postdoctoral fellow in the group of Professor Herwig Ott at the University of Kaiserslautern, Germany. And this is where actually our interaction started. He, at the group of Professor Herwig Ott, he studied the microscopic dynamics of ultra cold quantum gases in optical lattices. In 2015, he received a grant from the University of Kaiserslautern to study the coherence dynamics of Bose-Einstein condensates in optical lattices. From 2016 to 18, he worked on ytterbium quantum gases in optical lattices at the group of Professor Klaus at University of Hamburg, Germany. And this project was related to many-body physics in SUN symmetric fermionic quantum states. So I see your profile is actually very, very versatile. You have almost worked on every topic which is related to cold atom dynamics. So in 2009, from 2018 to 19, he also worked on quantum mixtures, dipolar molecules under microscope, and tunable quantum matter in optical lattices at the group of University of Innsbruck, a very famous group of Professor Hans Christoph. So it's an honor to have you here with such a wide and vivid, I would say, profile. I think a lot of people here and a lot of students are going to gain from your talk, which is on cold atom quantum technologies. So, Buddha, over to you. I think we can start, and a few people have joined here, but I see a few people there are also on the YouTube.
Mhm.
All right.
Okay, so first of all, so thank you very much for inviting me to this seminar. Actually, I also bought the ticket to go to Amritsar, but due to COVID, I had to cancel it. I hope in future I can definitely visit there. I've seen only the pictures. It's a beautiful place, and thank you very much for this introduction. Probably yeah, maybe I deserve a fraction of it. But hopefully when I do some experiment here, we would kind of see how things are going also in India here. And I'm also very much looking forward to it and the collaborations. But anyway, thank you very much. So now I'm going to start share my screen and then start showing the slides. So can you see my screen?
Yes.
Okay. So yeah. Yeah. So my main research tool or the technology what we use is based on cold atoms. So cold means the temperature is about a few microkelvin or something, which is basically like more than 1,000,000 times colder than the room temperature. So the room temperature is around 300 Kelvin or something, what we feel. And you know the temperature of liquid nitrogen is about 77 Kelvin, and if you go to helium, it's 4 to 2 Kelvin. And now what we do, so this is really much more colder than that, and this is a not a ambient cooling. So this is using lasers. So normally you could think that lasers could do only like heating kind of thing, destroying things, but you could also use lasers for good things and cool objects, especially atoms and molecules or ions. But you have to tune the frequency in a very precise way, and that's how we basically cool the atoms. Or so in our experiment we cool atoms to the ground state or the ground quantum state. So I will show them like why and how we do that. But what you see here in this picture, so at the center, this is a blob, so like like this green. So it's a blob of ytterbium atoms, so about 50 million or something, and their temperature is about 13 microkelvin. And the box what you see surrounding this blob is a vacuum chamber. So the pressure of inside this chamber is about 10 to the power minus 11 millibar, and this is much thinner air pressure compared to what we feel in the atmosphere. And the atmospheric pressure is about like a 10 to the power 3 millibar or something. And now the pressure inside this vacuum chamber is about a order of magnitude 10 to the power 14 lower, and we need that to protect this pure quantum state from any kind of unwanted collision, so that its lifetime is long enough for doing meaningful experiments. So now what is the impact of of the quantum technology on our normal modern lifestyle? So there should be a good motivation, right? So we definitely should do the fundamental things, but there should be a purpose behind doing things. So for example, if you look into the electric transport, or whenever these lights and fans they are running, so this needs electricity, and we know that this energy is a huge problem, because actually the loss of energy is a big problem when the power is supplied from a grid to the households or any industry. And now how to reduce this loss? So basically trying to find some cables which has almost no voltage drop. so kind so kind of something which is similar to a superconductor, but which works at a room temperature. The other thing is smart materials. The reason why we can do more or less everything what could have been possible using a large computer like 30-40 years back, so we have been able to do that using our mobile phone. The one of the big reason is that we could design and build smart materials. Also this advanced drug design. I mean, now with this COVID time, we do not have to tell what is the importance of having or discovering some new drugs for something which is very severe. So for that also, like, you have to find some smarter and very speedy way. So how you do that? So basically you have to look into some chemical reactions and then finding some optimized molecular structure, right? So that's basically drugs. So drugs are nothing but complex molecule which are formed by a set of atoms and molecules put together in a set of defined bonding. Some other more applied things is that optimization problem. So if you think of like a transport, then just if you take an example of different airports in India, or even if you go to the world scale, then how to optimize the parts of these flights in a most kind of optimized way. That's an issue. Like if you want to travel from maybe United Kingdom to India, and if you want to go to some specific city, then how to kind of have this flight paths optimized. So that's an issue. This problem can be in many other occasions also. And then secure communication. So there are also quantum states plays a major role. And then quantum sensing is also another very important aspect. It could be not only so optical clocks. So the optical clocks is something where you can measure the frequency in a most precise way. So you can build the optical clock using single ions or atoms, cold atoms trapped into optical lattices. But besides optical clocks, you can also make very sensitive gravity sensors or magnetic field sensors, and then you could make them useful for many applications. So now, how can we implement those technologies using cold atoms? So starting with this superconductivity, so that is basically something you can find in the phase diagram of Fermi-Hubbard model. And now if you cool fermionic atoms, and then you put them into optical lattices, you could kind of study the phase diagram of this Fermi-Hubbard model, which supports the existence of superconductivity. And you could also put them into different kinds of lattice geometry to study topological properties, which gives an idea of like a topological insulator or some new type of material. So you could really model using our cold atom tools. And regarding the molecules, so the very simple case of molecule would be to just take two single atoms and then put them together, and then trying to form the bond between them. So basically the simplest picture. So if you have A and B atoms, so put them together and then combine them to form the molecule. So this is a very simple case. You might think, what can you do with that? But if we understand this very basic case, then we could also go to the more and more complicated case step by step way. And now in the bottom row, you can see on the very left side, this is an array of roughly, I think, 49 atoms as the single atoms. So each of these kind of spot, they are representing fluorescence from a single atom. And these single atoms, if you look into the internal atomic structure, so they have different principal quantum number, hyperfine states, and so on. So you can use them for kind of representing the 0, 1, or all other relevant quantum states, what you need to represent a qubit. So you can also use such defect-free array of atoms for exploring quantum computing and implementing quantum optimization protocols and so on. Like in this second example of nanofiber atom trap, I mean, this is an example where you can make an integrated setup where you could kind of combine this cold atom sample with some optical fiber through which you can kind of transfer some atom photon entanglement. You could also do this in free space, and then by doing these things, you can kind of study the quantum memory. And then quantum memory is basically an analog of the classical memory. You know that when we do any calculation, we need to store our data for whatever purpose in between any calculation, or even after we get any result. So in this quantum communication, what is important, that if we want to make any long distance communication protocol, we should be able to store our information. And that's why this quantum memories plays a very important role. And then this optical lattice clock. So as I already mentioned, that these optical lattice clocks are probably the most sensitive device what we have so far, because you can measure with an unprecedented accuracy of 10 to the minus 19 on an absolute scale for any frequency. So so the outline of my talk would be the following. So first, I would like to focus on why and how to cool atoms and molecules to nanokelvin temperatures, and then some experiment using ultra cold atoms. So first of all, some dissipative dynamics using scanning electron microscopy of ultra cold quantum gases in optical lattices, and then quantum many-body physics probed on an optical lattice clock, and then some updates about what we are setting up now here at IIT Delhi. And then I would conclude with a summary. So first of all, why cooling atoms and molecules? So or maybe many of you or most of you have seen this picture of interference of electrons. So like if you have two particles, so like two electrons, and if you let them go through like these slits, and then in the screen you will see then an interference pattern. So whenever you see an interference pattern, then you should know that there is a wave nature connected to this particle. So, and now how do you measure the wavelength of or how do you characterize the wave nature which is connected to this particle? So that is characterized by the de Broglie wavelength, so which is given in this formula lambda dB. And if you look into this formula, then you will see, so it has only two parameters. So in the denominator, this small m, and then T is the temperature. So all other things are constant. So basically you can tune only these two things. And for the case of atoms or molecules, they are much massive in mass compared to electrons. So for the electrons, their mass is very small. So that is why even at room temperature, they are associated with some finite de Broglie wavelength. But for atoms and molecule, that's not the case. So on this right side picture, you can see at room temperature, so the associated de Broglie wavelength for the atoms are almost, I mean, there is almost no finite length. I mean, at room temperature, atoms move very fast. So like 300 meter per second, or sometimes even larger, which is basically the speed of the jet planes. So they are also moving close to the speed of sound, which is close to 332 meter per second or so. And now, as soon as you start to lower their temperature, what happens is that this de Broglie wavelength starts to increase, because you are kind of reducing T. So this T is sitting in the denominator, so you are increasing lambda. So that's the main purpose, to get a sizable de Broglie wavelength, so that we can kind of get the wave nature out of these atoms. And now when we reduce the temperature more and more, then at some critical temperature, so the de Broglie wavelength becomes large enough so that the wavelength of neighboring atoms starts to overlap. So that's actually the critical temperature where this quantum matter or the Bose-Einstein condensate starts to form. And then when we go to even lower temperature, a large macroscopic Bose-Einstein condensate forms. So that's the main reason why we need to kind of cool atoms and molecules to nanokelvin temperature, just to get their quantum mechanical behavior out. So now there are some experiments performed to check whether we really formed a matter wave, because if you do something, you want to also test it, right? Otherwise, how do you know what you are thinking that is true or not? And in experiment, we do that probably all the time. So that's why there was an experiment conducted in the group of Wolfgang Kettelare. So in this picture, you can see this interference of two Bose-Einstein condensates. So what they did is that they prepare a Bose-Einstein condensate, they split it in, and then they bring them together. So when they these two Bose-Einstein condensate came on top of each other, so they formed this interference pattern. I mean, you could think of a this Michelson interferometer, right? So in the screen, in the case of Michelson interferometer, you can see these fringes because that's a like a constructive and destructive interference, and then repeating that. So that's why the similar thing you also see here, but for the case of matter wave using Bose-Einstein condensate. So this kind of proves that at a very low temperature, so the matter is actually a wave. And that's the only reason why we could see this interference pattern. Okay, now where did all these things started? So although Arthur Raskin, he received the Nobel Prize in 2018, but he was the first to realize that one could kind of reduce the energy of an atom using lasers. So that was, I think, around 80 or something, and he was working with Steve Chu using sodium atoms. So the picture what you see here, so at the bottom of this this slide, so these are some pictures of sodium atoms which were cooled using lasers. And they are the first to realize that these lights, they provide some radiation pressure, and that is actually something which reduces the energy of the atom. So what is radiation pressure? So if you think of any comet, I am quite sure all of you have seen a comet, and if you look at carefully, so the tail of this comet is always opposite to the sun, right? And that is the case only because the radiation pressure on the comet's tail, um, so the light which is coming from the sun and going to the comet and to its tail, that pushes these tails opposite to the sun. I mean, that's natural, right? Because when the sun is shining the light from sun to the comet, then if there is a pressure due to the light, it has to be the opposite to the sun. So this is something what people have seen in the times before this laser cooling happened. But when such similar phenomena have been observed into the lab scale, then also it was kind of nice to kind of put all these pictures together to make a complete understanding. So Steve Chu, who received Nobel Prize together with Cohen Tanuji and Bill Phillips in 1997 for laser cooling and trapping of atoms. So Steve Chu was working with Arthur Raskin. And then they saw for the first time that one could use optical forces to cool and trap atoms. So, and the picture what you see below, that's the first picture of laser cooled atoms. That's the sodium atoms. And now, so I mean, after that, many very important development took place in the field. So, so 1997 there was a Nobel Prize for laser cooling and trapping of atoms, and then 2001 Bose-Einstein condensation. And you should know that this theory of Bose-Einstein condensation, it was initiated by S.N. Bose, Satyendranath Bose in India. So, and he did that for actually photons. which was massless. So, and he was working that time, I think in Dhaka and then West Bengal, in I think in Calcutta University or maybe Presidency University. And then he sent his paper to Einstein, and then Einstein derived the formula for massive particles. So, and that's why these two names, Bose and Einstein, came together. And then both the papers for photons and matters were published in some physics journal in Germany. So it was in German language. And then after that, there's so many decades, many people were trying. And then finally, around 95 or something, three people. So one is in MIT, Wolfgang Kettlere, and then two in Carl Weinman and Eric Cornell, that's in Gila in Colorado. They were succeeded in actually forming the Bose-Einstein condensation for the first time. But there were a few more key people. So starting from Dan Kleppner and a few other people, they were also kind of played a key role in formulating the strategy to how to cool this atom to nanokelvin temperatures. And then in 2005, precision spectroscopy and the invention of optical frequency comb was also awarded a Nobel Prize. So this is directly related to optical clocks. So how do you count the frequency, right? So when you have some frequency, you should be able to count it. So that technology was developed by Ted Hunch, and then a few more people. So they got also Nobel Prize for that. And then in 2012, actually, the Nobel Prize was for controlling individual atoms and ion. So in this case, the atoms was in the group of Serge Haros in Paris. So he was working with single Rydberg atoms trapped inside optical cavities, and the ions in the group of Dave Wineland in Colorado. And then in 2016, this was a topological phases of matter. So this physics has been explored not only in cold atoms, but also in other platforms like material science and so on. One thing I would like to mention that this is just kind of a recognition to the field, but the people, so of course the people who received the Nobel Prize, they worked on it very hard, very good, but there are so many other people who also contributed a lot, which actually grows the field in a like a exponential time scale. Yeah, so now with this introduction to the field, so how to cool atoms to microkelvin temperature? So first of all, we cool them to microkelvin and then we go to nanokelvin. So there comes this laser cooling and trapping. So if you think of a two-level atom, so it has two energy states, so like the ground state and excited state. And now you can think of an energy difference which could be related to some wavelength, let's say lambda. And now when this atom is moving with the velocity of jet plane, so you remember in the one of the first slides I mentioned that in the room temperature these atoms move with a velocity of jet plane or something like that. So at this very high velocity, you have to take into account the Doppler shift because of this velocity. So that's why you have to use some laser which is not exactly resonant, but this is slightly shifted from the resonance, which we call detuning, and that's due to the Doppler effect. And now the total energy of the atom at this situation is a sum of its kinetic energy, potential energy, and interaction energy. So kinetic energy is a large part of this total energy. So if we can reduce this kinetic energy, then in principle, we are reducing the total energy of the atom. And now the temperature is what? It's just a measure of total energy, right? So if you reduce the total energy, we are also effectively reducing the temperature. So that's exactly what we do in laser cooling. So we reduce the kinetic energy, and that's how we cool the atom. So now this is the case of one beam. So now if we add two beam from two sides, then you can imagine this atom would be kind of confined and cooled at a central position. But now think about one thing: when the atom is becoming slow and slow, so its Doppler shift is changing over time, right? But we are not changing. Actually, we cannot change the frequency of the laser along a space. So what we do is that we add a magnetic field gradient. So we just use two like a solenoid type magnetic coils, and the current flows in an anti-Helmholtz configuration. So we get a magnetic field gradient. And now what happens is that this magnetic field gradients then changes the energy shift into these atoms by the Zeeman effect. So that's how we keep the atom on resonant with the laser beam. And then after doing this pair of like this 3 counter propagating beam along a Cartesian coordinate plus this magnetic field gradient, we can trap and cool the atoms in all 3D. So at the end of this stage, we get a cloud of atoms which has a temperature of few microkelvin, and so that's the end of laser cooling part. And now when we want to go to nanokelvin, so then we load these cold atoms at few microkelvin in a optical dipole trap. So optical dipole trap is basically if you take a Gaussian laser beam and then you focus it to a very small beam OS, so let's say few micrometer, so maybe 10 micrometer or something, and then you will get a very tightly focused spot where you can trap atoms. Basically, this is like a parabolic potential, and you can even model it using harmonic oscillator. And then this is basically a trap which you can think of like a when you have a hot coffee or hot tea in a coffee mug, right? And then if you just think of a coffee mug and then you just wait for some time, you will see that hot particles are evaporated from the upper surface. Its energy becomes low, and that's why its temperature. Technique's name is also evaporative cooling, but we do it little bit in a forcefully. So like if you kind of blow some air with your lips on the coffee mug, so something similar we do. But for that we reduce the height of this dipole trap by reducing the intensity of the laser. And then after throwing some hot energetic particles, we end up with a very cold sample at a temperature of a few nanokelvin. And you remember that in one of the first slides, I showed you that once you cross the critical temperature, so the de Broglie wavelength would be large enough to form the large matter waves in the form of Bose-Einstein condensates, or if you start with fermions, it would be a degenerate Fermi gas. So that's how we end up with this quantum gas, which could be either Bose-Einstein condensate or Fermi gas, depending on which atom and which isotope you take. Okay, and now we have to measure temperature. How do we do that? Normally, if we have like if we got fever or something, we use a thermometer. But for the case of atoms, we cannot insert a thermometer, right? Because first of all, the atom is into a vacuum, and if there is even some other atom which hits this sample, that would be destroyed. So we have to come up with some other kind of method. So what we do is that we kind of switch off all the traps, and then the atom starts to fall under gravity. And when that trap, when this atom is falls under gravity, so there is no trap, so this atom starts to expand. So we can measure how much it is expanding, so we can get this time series. So imagine just we have a xy plot, and then this the horizontal axis is representing the time of expansion, and the vertical axis is representing the width of this cloud. And then fitting Maxwell-Boltzmann distribution to this plot, we can extract what is the temperature. And now we can ask the question that why Maxwell-Boltzmann distribution? Because Maxwell-Boltzmann works only for the thermal atoms. But when we have already crossed the quantum phase transition, then how can we do that? So we could do that for the following reason. So remember I showed you this parabolic trap. So this one. So at the very central point of this, so the density is maximum. So that's why it fulfills the condition to form a quantum gas. But at the wings, so where the density is not much, so there, although the temperature is same, because the system has to be in a thermal equilibrium, so the temperature of the atoms at the central part where density is maximum is same as for the atoms which are in the wings. But the atoms which are in the wings, they do not form the quantum gas because their density is not enough to fulfill the condition of a quantum gas. So that's why the atoms which are at the wing, we can use them for finding out the temperature using the Maxwell-Boltzmann gas. Okay, so that's how we can find out the temperature. And then so finding or the characterizing the trap, that is also very important, because for whatever calculation or measurement what we do, we need to put the harmonic oscillator properties, right? Because I mentioned you that these traps, you can model them, we can model them using a harmonic oscillator. So for that, what we do, basically that's shown on the right side. We just excite the atom cloud inside this potential, and then we measure the position of center of mass as a function of time. And with this center of mass oscillation, we can extract by fitting some sinusoidal curve what is the oscillation frequency, and that is exactly the harmonic oscillator frequency. And that's how we can characterize both the temperature and the trap properties, right? And then we can use these things for any further measurements or calculation. So how does a typical setup look like? So I mean, this is a setup what you can see. So this is a setup from my Hamburg lab. So where we had a optical lattice clock using ytterbium atoms. So ytterbium is a very colorful atom. In some of my later slides, I will show you some level structure. So that's why you can see various colors of lasers. So it has green for the main transition at 556 nanometer. So the yellow is 538 nanometer, 578 nanometer for the clock transition. Some blue, which is not shown in this picture, but that's for main cooling transition. And this pink one, what you see, this is at 660 nanometer for some state-dependent lattice, and also had some more infrared lasers for far-off resonant dipole traps. If you look at a closer look, then you will see that this is basically an arrangement of several mirrors and lenses and apertures and so on. So all these elements, so we just put them together in a very planned way, and that's how our setups are formed. So if you ever want to work into the experimental aspects of this field, then you have to know very good optics. So how to shape a beam, or how to focus a beam, and how to kind of change the size of a beam using a telescope and such things. And if you know these basic parts, you can add them one after another in a planned manner, and then you can set it up. So that's all basically. So you see that we start with a very basic thing, which is simply very basic, and then we just add one after another, and then we form it. It's of course takes some time. It's not a one-day job, but if you follow this planned path, then you end up with a very nice cold atom setup. So now this picture I have already shown to you, and after doing all those things, we get such a very nice cold atoms. And now let's look at how we did some experiments using cold atoms. So first of all, scanning electron microscopy of ultra-cold quantum gases in optical lattices. So main motivation for studying such experiment was the following. So we wanted to find if there is any steady state in such quantum systems. In principle, steady states could be found in the places where you have at least two parameters. So one is loss and one is gain, right? You can even find it in a kind of you just think of a water glass or something, and then if you make a hole which is inlet at the like upper part of the glass, and then if you make another hole which could be through which maybe water can come out, and if the rate of incoming water and the outgoing water is same, then you would basically find a steady state. This is different from equilibrium, right? Because there is always a dynamics going on, but still you have a constant water level inside this glass. So the similar thing is feasible in many places, in the case of heat conductance, current flow, even in share market, and even into the quantum systems. So in the quantum systems, if you have some, for example, decoherence is a big problem for all kind of quantum technology. And decoherence takes place because there is some loss or dissipation channels which destroys the pure quantum state. So sorry. And now if we can find some steady state, then you can imagine this state could be an starting point of various quantum technology applications. It could be quantum computing, quantum communication, quantum sensing, and so on. So there was some theory proposal which was suggesting that if some dissipation is present into a quantum system from the beginning of the measurement as a constant parameter, then after some transient time, the whole quantum system should go to a steady state. So this is something which was motivating us to look into such phenomena in an experimental scale. And so actually in this left side picture, what you see, this is kind of a fixed points. So of this contour. So now you can think of this as a IV characteristic or whatever, which involves a flow as a function of time. And then you will see, you will get some fixed point, which is basically, if you think of this loss and gain. So in this curve, there would be some point where this loss and gains are kind of balancing each other. And that's why these points are called kind of a steady states or fixed points, where the dynamics would be kind of giving you a steady situation. Okay. So, and we could model such dynamics using some Lindblad formalism. So in this formula, what you can see, this rho dot, this is representing the density of the states. And then there is some imaginary term plus some imaginary plus Hamiltonian terms of the system plus some Lindblad operator using this Liouvillean form. And this part actually models the dissipative environment into the system. So now our experiment was the following. So we used a scanning electron microscope. So we had a Bose-Einstein condensate of rubidium, and we just used this scanning electron microscope to image the Bose-Einstein condensate first of all. So what happens is that when you send this focused beam of electron, it creates some like atoms. It knocks out the electron from the last orbital, and then it becomes a rubidium plus ions, which we can detect into our detector. And this is definitely helps us to make a very high resolution image. So in this picture, you can see on the right side, so this is an array of this dot. So each dot is representing about 80 atoms in an optical lattice. And the distance between two dots is about like 547 nanometer. So you can see this is a very high resolution imaging. And in the picture below, you can see we have selectively and deterministically removed almost all atom from some of the sites. And in this picture, this is just for demonstration, but later we use the same technology to induce dissipation in the system in a controlled way. So for this dissipation experiment, so we first created the Bose-Einstein condensate. So if you look at this first part, this time versus S is the depth of the lattice. So we first created the Bose-Einstein condensate, and then we freeze the distribution by making the potential depth very high, and then we removed almost all the atom from a central site. And then when we reduce the lattice site, then the atoms from neighboring sites starts to tunnel into this site where the atom number was low, and then we measured the filling rate, and then from there we deduced what is the steady state populations as a function of times and so on. So what we get is the following. So this wells, what I was mentioning, so you can see here in this first part. So you see all these connected potential wells, and the central one where we had this incoherent loss mechanism due to the constant operation of the electron beam on a central site. So first we started with like almost no atom into this central site, and then second, without removing atom with this central site. That was the initial condition. But during the measurement, we always keep some dissipative electron beam on. And these two results you can see into this plot below. So for the case of red, so this is something where the initial condition was the following, that we removed almost all the atoms from the central site. And then you see after some maybe 80 or 100 milliseconds, the system reaches a steady state. And then in the other case, when we did not remove any atom at the very beginning as initial condition, then also this blue points, so then also we got a steady state, and then that was something what you can see is around 80 to 100 milliseconds. So now we did this experiment for different dissipation strength. This dissipation is when the measurement was going on, and that is what we plotted here. So what you see here on the x-axis, so this gamma shows the dissipation rate, and on the left side this is the filling level. So the filling level of the atom, so that's basically this one, right? So filling level is basically what is the filling of the atom at the steady states, means around 80 or 100 millisecond or in that range. So this part of filling is plotted in this plot in the y-axis. And what we see is that for very low dissipation, so whatever is the initial condition, so the site is always 100% filled. So that's why this filling level is 1 here. If we look into very high dissipation, then also both the initial condition comes to a same steady state, although this is different from this completely filled one. So the completely filled one you can think of like a superfluid response, because in a superfluid, whatever you do, the system should be always fill up, right? So kind of a frictionless flow. Sorry. But now interesting happens in the medium part, in the middle part, where depending on the initial state, so the system we could get two different steady states. And now you see with this experiment, we could generate different kinds of steady states by varying the parameters, the gamma, that's the dissipation rate, and the initial condition. So I think that was quite interesting and important, because now for any type of quantum computing experiment, we could try to find such steady states using maybe an array of qubits. And then that would provide us a robust starting point to implement any quantum gate operations. So, okay. Now let's talk a little bit about the quantum many-body physics problem and optical lattice clock. So I was already mentioning you this alkali earth atom ytterbium. It has several level structures. So this is a little bit more rich and complicated compared to the alkali atom, and we could do several things. So such as the orbital magnetism, or Kondo lattice model, or topological superfluidity, or spin orbit coupling. And we should mention that the optical lattice clocks, they are all built on either ytterbium or strontium atoms. So that triplet P0 state, this is called the clock state. And the transition from singlet S0 to triplet P0, so you see in both cases J, this angular orbital quantum moment, angular quantum number is 0. So basically this is a almost forbidden transition, and that's why it's theoretical line with this millihertz or something. So, and now the challenge is, how do you do spectroscopy of this? So for that, we have to build a special laser which has a very narrow line width. Otherwise, you would not be able to excite this transition, right? So that's the main challenge of this experiment. So let me show you a few slides of how we built this laser, this very narrow line width clock laser. So we actually use some fabric arrow cavity, and then we lock this laser's frequency to this fabric arrow cavity. And now we stabilize the length of this fabric arrow cavity in a very, very good way, so that there is no drift or anything. And when we lock the laser to this cavity, then the line width of this laser can be even below 1 hertz or something. So this is what we could do, and then we could kind of characterize the some properties of the cavity. So this is a characterization of the temperature of this cavity, because this if you want to keep the length constant, you have to kind of know what is the thermal expansion of this cavity material, and then basically you have to put it in a temperature such that its expansion is minimal or almost nothing as a function of change of temperature. Because if the temperature is changing even 2 or 3 degrees, and you will get a very small expansion, but that would already be enough to kill the performance of the laser. So you have to keep it in a constant in a way that it almost does not change anything. So that exercise we did by doing some laser spectroscopy, kind of locking the laser to this cavity, and then doing the measurement at couple of different temperature, and then finding out in this right side, you see there is a crossing. It looks like a parabola, and then the top around 32 degrees something. So you see that there was a crossing. So this means if we can put our cavity temperature around that point, then the expansion would be minimal, and that's why the cavity expansion effect would be minimal. So that is a very important part, or probably the most important part of designing this laser. And now when we measure the full width maxima of this laser when it is locked to the cavity, then we find it so like 0.835 hertz or something, which is below 1 hertz, which is very good just for one sweep. And when we average it over 30 second or something, that's a half a minute, then also the full width maxima was like a 4.45 hertz or something. So this is very good as a clock laser. And now if we have such a laser, then we could do spectroscopy of some very narrow line width transitions. So you could think of what would be the problem if we take a laser which has a full width maxima of few megahertz. So you can think of like just imagine couple of points, and now across this transition, then if you have a laser width which is megahertz, then you would not be able to distinguish what is happening at a hard scale, right? Because it would be really a broad thing, right? So that's the point. So that's why you have to kind of minimize the line width of the laser in a way that you can really see the change what is happening at the hard scale. Okay, and now I was talking briefly about the optical lattices, so maybe I spend maybe 1-2 minutes or so on this. So optical lattices are basically it's an interference pattern formed by laser beams, which are really defined in frequency and polarization. And then if you have if you made some interference pattern into using such defined light beams, then you can have like destructive and constructive interference. And then depending on the wavelength of the light, the atoms can be trapped into either into this interference maxima or minima. And then based on like if you use just two counter propagating beam, then you can have a 1D optical lattice. And if you have like a 2 or more, then you can have like a 2D or 3D and more and so on. But you could also do like optical trapping, like optical tweezers, for example, or maybe in a honeycomb geometry by changing the this interference patterns. And now, so this is an example of a result of an optical clock spectroscopy. So for doing the clock spectroscopy, you remember that I was showing you how to prepare like a quantum gas to nanokelvin temperature. So after preparing that, we load the atoms into these optical lattices, and then we did this clock spectroscopy. So for that, what you see that in this picture, so we scan the frequency to this range. So the horizontal axis shows the clock laser detuning, and the vertical axis shows the relative ground state excitation. And then you see that the line width of this spectroscopy was around 50 hertz. So that is very narrow. Yeah. So we would, and if you, and now maybe here it would be even more clear. So if you switch the x-axis, so this clock laser detuning, you see that this is very small. So total is minus 0.2 to plus 0.2. So that's basically sorry 400 kilohertz or something. And now if you imagine if you have a laser which has a width of 1 megahertz, you see everything would be filled, and we would not be able to resolve this transition, right? So that's the reason we need to get such a very narrow line width laser. And it shows that the laser we had, we were able to do able to resolve such clock transitions, which is good for studying any many body physics later on. And here actually we did the spectroscopy with two components gas. This means using two different spins. I'm not going into too much detail of this, but the main message I would like to give is that with this technology, then we could do several studies. So including study of spectral line shape or spin orbit coupling using optical transition, and also preparation of specific quantum states. Now finally what we are doing here, so here we are starting our new lab. So basically we are working with cesium atoms, and then we'd like to explore the quantum computing using neutral atoms. So there are a couple of advantages of using neutral atoms for quantum computing. So first of all the atoms are identical. I mean, even if you are taking an atom, if you just imagine that someday you could go to moon or you can go to Mars, and then also if you want to do this experiment and then you take cesium atom, they will be exactly same. I mean, it's same for all atoms, because this is a gift from nature, right? In the case of like maybe other silicon qubits or the superconducting qubits, that's not the case because you have to fabricate the material. But for the case of ions or atom, they are identical. So that's a very good point. And now the miniaturization is also another thing. So for the case of ion and atom both, so the scalability is good. Okay, I should be a little bit careful because for the ions, so if you use one ion trap, then you could trap about like 50 to 70 so far. But now if you want to kind of increase, so these ions are basically in a electrostatic trap, so in 1D chain. And if you want to increase, then you have to increase this number of chain. So you basically have to make more and more ion traps, and then you have to somehow combine them together like a parallel processing. Um, okay, but for the case of atoms, there is an advantage because we can trap atoms using optical tweezers. So we just have to make another array of tweezers, right? And then we can make not only 2D but also 3D arrays of tweezers. And that is a very good thing. We have been doing that using optical lattices for our many body physics. But there was one missing thing, that is the following. So whenever you want to do quantum computing with arrays of atom, it should be defect free. And that was not the case because loading from magneto-optical trap to sing this optical tweezers or traps is a determinist is a probabilistic process. So normally 50% loading should be there. But now in last few years, there is a new technique which came. Like just imagine you want to start with a quantum computing protocol with a 5 by 5 array. So what we do, we start with a 10 by 10 array, and then we go to a subset. So what happens is that in a second step, we bring the atoms which are staying this outer of this 5 by 5. We just use some moving tweezer, we pick them from outside, and then we fill the gaps into this 5 by 5. So that's how we make an like a defect-free array of qubits. And then this is a ideal platform for exploring quantum computing. So the this is about the miniaturization and scalability. So there is no dilution refrigerator or large freezer is needed as we are doing laser cooling. So remember the glass cell I was showing inside which we have trapped these atoms. So it's something like that. Of course, we need some lasers, but this can be also put in a miniaturized shape, and you do not really need a large dilution refrigerator. So the noise insensitivity for atoms are also quite important because atoms are neutral, unlike ions or any other qubits. So atoms do feel definitely the stray magnetic and electric fields, but as they are neutral, their response is very, very low. And that's why their coherence time is very good. So actually, for the case of optical lattice clocks, so the coherence time is really very good, probably one of the best. So that's why they are also providing very good coherence time. And if our coherence time is good, then the number of gate operations we can do, that would be even more and more, right? Because if the coherence of the qubits are lost, then whatever operation we do, that would be not of any meaning. Okay, so now the type of entanglement we can you still see my slides?
No, it just stopped.
Yeah, I got a
wanted-
message from here, so maybe I have to
Okay.
reshare again.
Yes. Oh, I was trying to take some screenshots and maybe I clicked something. Okay.
Okay,
Yeah, maybe. Yeah, I'm sorry.
no problem.
Yeah.
So, okay. Yeah, so for engineering multi-qubit gates, we need to bring at least two atoms together or two qubits together, and then entangle them. So that we can do by either bringing two atoms and then via spin exchange interaction or via Rydberg excitation. So the Rydberg excitation is something as the following. So we can excite the atom to a principal quantum number which is very large, maybe n equals to 50 or even more. So what happens is that these principal quantum numbers basically define the orbitals in which the atoms can go. And now when we excite them to this very high principal quantum number, so their wave function becomes large. It becomes actually macroscopic of few micrometer size. And now we can imagine if we can place two optical tweezers loaded with single atoms, at a distance of few micrometer, let's say 5 micrometers or so. And then if we excite them to Rydberg state, then these two atoms wave function would be interacting with each other. And this interaction we can use for implementing quantum gates. So that's the recipe for engineering multi-qubit operations using neutral atoms, qubit arrays. And there could be several applications starting from quantum optimization, quantum error correction, quantum various types of quantum algorithms, and it could be applied to like wireless network design or air traffic management. And of course, the big goal is to design like a universal quantum computing architecture, which could be also programmable. And until last couple of years, there was not too many direct quantum computing activity going on using atoms, but there were many like quantum simulation and such on. The main reason was this defect-free requirement I was mentioning, but this thing is now we know how to do it. And there are also many startups also popping up using this, so that's really coming up as a active field. And few months back, actually, there was some article which was highlighting in Science actually that neutral atoms may rise as the dark horse qubit candidate, right? And we are actually exploring this field. We are setting up our lab, and yeah, that was all. So in the summary, I showed you how to why and how to make quantum gases or cold atoms at microkelvin and nanokelvin temperature, some results on dissipative quantum systems, some results on optical clocks and clock spectroscopy. And then in general, I was trying to show you that these ultra cold quantum gases and cold quantum gases trapped in optical lattices and traps can provide a versatile toolbox for implementing various types of quantum technology experiments. So the main technology we use is based on atomic physics, molecular physics, optical physics, and then we can explore various types of quantum many-body physics, quantum chemistry, and various other quantum optimization things, and also fundamental physics. And then yeah, also various types of quantum information processing protocols. So this is the team what we have now. We had a couple of very nice PhD students. It's really nice to work with them, and the MTech, MSc students, and some good BTech students also. And then we also so we are an experimental group. So we develop the hardware. And now, like if you think of it just a classical computer, you just also have to know the software like for coding it, right? So otherwise, how do you kind of do your calculation? The very similar thing works for quantum case also. So you need a hardware for implementing your softwares, and you also know how to implement this software. So the quantum algorithm design or the quantum protocol design. So that's why you also collaborate with various collaborators. Also, we have a collaborator with Professor Arora. So yeah, and that's how we try to make nice things. So that is what I wanted to show it to you today, and thank you very much for your attention.
Yeah, thank you, Professor Sandra. That was a very nice talk. I mean, you included so many fields which are related to cold atom physics. That was very nice. I hope the audience here are convinced with me. We have a couple of questions on YouTube and few questions on WhatsApp were sent to me. So
Sure.
shall I read them out?
Yeah.
Am I audible to you?
Yes, I can hear you.
Oh, all right. Okay. So the first question is from Ritvik Srikantham. He says, can you please explain how you achieve the parabolic potential in the evaporative cooling in lab?
Yeah. Sorry. This is basically done by using a Gaussian beam first. So and now just imagine a Gaussian beam. It's a collimated one, and now if you put a lens, what will happen? So at the distance of the focal length, you will get a focus, right? And now after the focus, it will start to expand again. But at the focus point, you will see that the intensity will go to a maximum, because the intensity is the total power divided by the area. So the total power is same in the beam, but the area becomes very small. It's actually scaled with the square. So that's why the intensity would be maximum. And now if you think of the like the polarizability of the atoms, then depending on the wavelength and the atom's property, this atom would be attracted or repelled by this potential. So normally, if we use a Reddition trap, then the atoms are attracted to this potential. And now when you are using this Gaussian beam and then this is a focus, then it forms a potential which you can model using a harmonic oscillator, which is parabolic in nature. So that's how we do that in the lab. So just take a Gaussian beam, use a lens, and then focus it down to few micrometer, and that's what we get. And of course, this focus has to be inside this vacuum. Yeah.
Okay, thank you. Another follow-up question from Ritvik is, how you estimate, how about the estimation of temperature?
Yeah. So as I was mentioning, so so we use Maxwell-Boltzmann distribution. So now, if you look into the Maxwell-Boltzmann distribution, you see there is some constant term and there is a temperature term T. And now, if you fit, so if you take the picture of an atom cloud, you can do this by using some resonant laser. And then so like if I go to, yeah, even if here I have it. So here, so you see this is kind of a Gaussian in nature, but it's a 2D Gaussian, right? And if you integrate along any one of the axes, you will get a Gaussian type of curve. So, and now you can fit this curve using Maxwell-Boltzmann distribution, keeping temperature as a free parameter. And then from there, you can extract what is the temperature. And as I mentioned you that if it's a Maxwell-Boltzmann distribution, just imagine its temperature is 10 microkelvin. And then you have another cloud which has a temperature 2 microkelvin. And then if you let both this cloud expand, then definitely the 10 microkelvin will expand faster as a function of time, right? And then we just use this time series to extract the temperature.
Something what is done in time of flight experiments and all, like just allowing the atoms to fall and then see how much time they covered and then finding out temperature from it. Something like that?
Yes, yes.
Okay, okay. Thank you. So another question from Ishita is, I mean, she's curious to know more about Rabi oscillations and Rabi frequencies. I mean, the basic concept.
Yeah. So the Rabi oscillation is a probably one of the very fundamental information we have to do for characterizing the coherence, also creating the coherence, and also different types of state measurement. So what is done is the following. So just think of, we have one atom with two levels, so the ground state and the excited state. And now if we send the laser for a very short time, so the atom from the ground state will be excited to the excited state, and then after that, after some finite lifetime, it will decay to the ground state. And now if we increase the time in a way that so the laser beam is constantly going to the atom, what happens is that the population from the ground state to the excited state will start to oscillate. And this is something which is called Rabi oscillation. And depending on for how long we are sending this light, we can create superposition states. For example, if we send a time which is actually called a pi/2 pulse. So this is basically meaning that we can kind of create a superposition of the atom from the ground state to the excited state, right? On the other hand, if we send a pulse which is called actually pi pulse, it depends on the intensity. So the Rabi, there is a term called Rabi oscillation frequency that defines the strength. It depends, and it comes from the intensity of the laser which is involved into the Rabi oscillation. And now if we make it pi/2, then we can make a superposition of the atom between ground and excited. And if we make it pi, then we can completely transfer the population from ground to the excited state, or the vice versa, to excite or de-excite. So this is roughly the concept of the Rabi oscillation.
Okay, so instead of giving a pulse, I mean, if the laser is continuously given to the atom, then they'll excite and then come back, and then excite and then come back, and so on.
Yeah,
okay.
Yeah.
That's interesting. Final question: if some audience from the Zoom has some questions, they are free to ask. They can unmute themselves and ask questions. As there's one more question which I would like to take up from the WhatsApp.
Yeah.
So anyone from the Zoom, if they're interested in asking a question. Okay, so Boda, the last final question which I have is related to this is from a BSc student, and his question is, when you talk about locking the laser to cavity, when he says, I'm not very familiar with this terminology. What does locking the laser to cavity mean?
Yeah. So so basically, I mean, we use the word locking, but fundamentally, what we would like to do, you'd like to. So just imagine we have a laser with a frequency some terahertz. So there would be some last digit on hertz. Yeah. So our main goal is to reduce the how to say, as a function of time, we would like to keep the frequency as it is. And now by locking, we mean that locking the frequency of the laser, right? So that can be done in various ways. So if you think of a signal which has a let's say it's a dispersion like signal, this means so it can have a zero crossing, and now you can use such a signal as a error signal, and then you can, using some electronics, you can set the condition as the following: whenever the signal goes more than zero or less than zero, so the electronics should force the whole laser system to go back to this zero, and that's how you could reduce the drift of the laser frequency as a function of time. So the basic concept of locking means you would like to reduce the drift of the laser as a function of time. Okay. So the last digit, so if it is in, so for the case of clock, the drift was less than 4 to 5 megahertz as a function of, sorry, not megahertz, 4 to 5 hertz in a time scale of 30 seconds or something. And if you wait longer and longer, this drift will be more and more. But if you see any laser which is not unlocked, then it would be in a scale of few, it could even be gigahertz. So by locking means we kind of use some reference cavity for generate this error signal, and then we use some electronics to reduce the frequency drift as small as possible.
Okay. Thank you so much. I think we are already, uh, yeah, we are already short of time now. So unless anyone else wants to interact or give some comments, I think I would like to thank the speaker today. So yeah, okay. So thank you, Professor Santra, for joining us and giving a wonderful talk. It was very nice and very informative. And I hope everyone here had a wonderful time and they learned something new. Thanks a lot for accepting our invitation, and
Yeah.
I hope we see you sometime in Amritsar soon.
Yeah, thank you very much. It was really nice. So I hope also we can see it